Saxon Advanced Mathematics, lesson 42. This is a beastly lesson. I'm going to take steps to make it less beastly because last one was pretty beastly and I don't want to tax your soul. Okay, we're talking about circles today. Ta-da! I'm going to be very practical and to the point. We're going to skip some of the theoretical mumbo jumbo and just get to the point. But first I want to remind you of our butter sculpture metaphor. Imagine that this marker is a perfect straight line, and imagine that my fingers are so skinny that I can hold it just at one point, all right? And imagine that without using another hand, I could rotate this marker so that the tip of it was going in a circle. And notice what's happening at the other end of it. That's also making a circle. If you can imagine those things happen with perfect mathematical accuracy, there are the two circles that the tips of the marker were making. There's the variety of paths that the marker was making, right? As I was twisting it, it was making kind of a shape like that. And right there is where I was pinching it. This is called a conic section. And what's cool about it is that it is the source of quite a few different shapes that we're going to talk about in our geometry travels. What I'm going to do is I'm going to draw 4 of these, and I want you to draw them with me. And as we're drawing them, I want you to imagine that these are butter sculptures. Have you ever seen a butter sculpture? They're pretty cool. And I'm in the mood because Great British Bake Off just wrapped up this week. I don't know if you're fans, but I am pretty into it. And so I'm thinking of cooking metaphors. But these are butter sculptures. They have been shaped into 3D perfection by some amazing culinary boss. And they've been sitting in a freezer. They're ice cold and they're all the same. I just wrote that by the first one, but they're all the same. And what we're gonna do is we're gonna take a blazing hot butter knife and we're going to cut them, all right? The first one, we are gonna cut right through there. And when we pick it up and look down into it, the shape that we're going to see is a circle. We're going to talk more about those today. But that's the shape we get when we slice right through that hot buttered sculpture and then we take it and look down at it, all right? What about if we take our butter knife and this time instead of cutting straight across, we cut on an angle. Now when we look down on it, we're going to see more of an ellipse, right? It's not going to be perfectly straight because we didn't cut perfectly straight. It's going to be more of a egg shape, right? We call that an ellipse. We don't call them ovals anymore. That was kind of a grade school thing. We call them ellipses. We're going to be talking about lots more of them. What if we take our third butter sculpture and we chop it through here? This is the bird's eye view down into it, these smaller pictures. If we look down into it, we're going to have what we call a parabola, right? That side will be gone and we'll just have this U sort of a shape. Whoops, parabola. We fooled around with these a little bit. We're gonna do more. And what if we slice it like that? Well, that's going to be even crazier because as we take it and look at it, we're going to get that, which is called a hyperbola. I call it the basketball shape. It looks like the lines on a basketball, right? So, and we'll do a little bit with this, but we're going to spend more time with these 3 shapes. They're a little bit simpler. So, let's focus on circles. And here's what I'm going to do. John is going to give us a great big theoretical workup on how we get this formula. I'm going to give you the equation of a circle. And I'm going to tell you just enough theory to be dangerous. All right, and I'm going to draw a picture in just a minute, so don't worry. When you first see this, you're going to go, what is she even talking about? But when you see the picture, it'll make more sense. Okay? I'm using a new marker color. You know I prefer to use green so that I can keep track that you're the green class, but I've got all these random purple ones. So today we're using plum. I hope it makes you feel very fruity. Okay, this is the equation of a circle if, let's draw the picture, the center of our circle is at a point that we call HK, and that's not perfect, but pretend it is. Oh my gosh, it's so not perfect. A point on the circle is XY. So we can substitute these values in for our equation. Okay, and this is all based on the distance formula, right? Because if we're trying to find the distance, I don't want to get into this. Let me just say that. The distance formula measuring from these 2 points allows us to derive this value, okay? So H and K are the center of the circle. This is a point on the circle. And R is the radius. Okay? If you're really dying to see how we use the distance formula to derive this, then by all means go look on pages 302 and 303. And the first example will load it up for you, and that'll be great. But I don't want to make you crazy. This is also, by the way, the standard form. We don't have as many different forms of the equation of a circle. Remember that lesson we did, the equation of a line with like 5 different forms? There aren't so many with a circle. Okay, but I will tell you, this is the standard form, and then the general form, where is it? Here it is. Well, let's do it in this one because we're gonna figure it out in this one. Instead of giving it to you and making your head wobble, let's just do it. Find the standard form of the equation of a circle with the radius of 4, whose center is at -3, 3. That's the center. Then write the general form of the equation. Okay, so we know how to do this. First we write the standard, and we've got it right here. It's x minus h quantity squared plus y minus k quantity squared equals r squared. And this kind of makes sense because look, h is the x value of the point at the middle, so we pair it with the x. K is the y value of the center, so we pair it with the y. There's our formula. All we have to do is take our points and plug them in. R squared, we know, is 16. And I'm just going to label these. H and K are our center, so that means that H equals -3 and K equals +3. So now I can go x plus 3 quantity squared, right? The 2 minuses cancel out. Plus y minus, this is the +3. It's kind of confusing because this is the same number. But the negative goes with the h, which goes with the x, so that's the positive one. All right? This is our standard form. So that's the first part of the answer. Then John asks us to find the general form. And the easiest way to explain the general form is to expand the binomials. So let's see if we can do this in our heads. Squaring this would be x squared plus we add this for the middle term and then we multiply it by itself for the end, right? So that would be that. X squared plus 6 is 2 of those and then multiply 9, okay? Plus, now we have to do this one, y squared minus 6y plus 9 and then equals 16. And then for the general form, we're gonna do this. We're gonna pull this over So actually I'm gonna say minus 16 equals 0. I swam that over this way. Now all we have to do is combine them, and this is the order that we use. X squared, got that one, plus y squared. Now we do the middle terms, plus 6x minus 6y, and then we lump all the numbers together. Plus and plus is 18 minus 16 is plus 2 equals 0. So that is the general form. Okay, so there's, rather than having like a set formula for the general form, we just multiply these out and then organize them this way. First the squares, then the powers of 1, then all the numbers smushed together and a 0. All right? Yay. All right. Okay, that's all for the equation of a circle. All right? Remember that the general form, this is important to remember. Write this in your book. Expand the binomials. And organize. Okay? Beautiful. All right, now let's switch on to another topic. Second, my battery is misbehaving. Well, I better just go fast, right, before my phone dies. It's plugged in, but it's not reading as a charge, so. All right, constants in exponential functions. Let's just dive in and show you. They look horribly scary. I'll show you how to make them fun. 42.3, sketch the graph of the function y equals 3 to the minus x. What the heck is that negative sign doing up there? I don't want any part of that. That is scary and weird. Well, here's what we're going to do. We're going to use what we know about fractional exponents to calm this down. So what we're going to do is we're going to say y equals 3. Now we know that with the power rule, if you're taking something to a power and then to a second power, you multiply them. So if we can separate these two, we can back it down into this format. So we're going to use this backwards, and we're going to recognize that this could be 3 to the minus 1 raised to the x, and that 3 to the minus 1, well, we can fix that. That becomes 1/3 to the x, right? That is not so scary and not so hard. We know that it's an exponential equation. We know that it's either going to go like this or it's going to go like this. This is for numbers greater than 1. This is for numbers less than 1. This is less than 1. Bases, right? Right? If the base of the exponential equation is greater than 1, it's going to go up. If the base of the equation is less than 1 like ours, it's going to be tipped to that side. So when we sketch it out, we know that it's going to cross at 1, 0. It always does. This is just going to tail down, right? We know that this point is going to be 0 and 1. Sorry, I'm writing that the wrong way. Because if we make a quickie table, x if x is 0, then this is 1/3 to the 0, and that's equal to 1. That point is always true in an exponential graph. But let's take x is related to -1. That'll be 1/3 to the -1, and that's going to be 3, right? So this, -1, 1, 2, 3, there's our first point, and that's all we need to do. Okay, so finding a second, this point will always be there. You don't have to calculate it. That's a gimme. This one point is what we need to do to graph it accurately, and that one point is all we need. But the real trick of this problem is learning to use the power rule to simplify this so that we can get a number we can live with. Example, there's 2 more. Example 42.4, sketch the graph of the function y equals 1/2 to the 2x. Again, our goal is we just want to have that x by itself on the outside like we did here. So we'll rewrite this as 1/2 squared. Actually, we technically need it like that. So this square relates to the whole thing, and then it'll be to the x. So that's the way we have to write it. But there's our 2x, right? We just broke it apart using the power rule. So now we can calculate the square of 1/2 as 1/4, and there's the x, and then we can graph it. Again, we know that because the base is less than 1, it's going to go this way. We know this is going to be the magic point where it switches here at 1, and it's 0 and 1. I want to put that 1 first, and that's so very wrong. And then we know that if x is equal to -1, then that's going to flip this, and y will be 4. So if that's -1, I'm just going to sketch in 4. I'm going to put 3 by that one because that helps. And then it goes up a bit faster, doesn't it? Okay, so that's the answer to this one. This is correct. We were asked to just sketch. That's the main thing. And then here's the last one, and it's got a new wrinkle in this crazy exponent mess, but I'll show you. Example 42.5, sketch the graph of the function y equals 1/2 to the minus y minus 2. That's a lot, right? This is a mess. So we have to be really crafty in the way that we do this. This is going to be, we're going to take the 1/2. First, we're going to deal with this much because we know that, here's another thing, right? If we're adding or subtracting, then we can use the product rule to break that apart. So first we're going to deal with this much. That's going to be 1/2 to the -1 to the y. I'm sorry, it's supposed to be an x here. So this is the x, right? On the outside. And then this part we'll do as 1/2 to the -2. Here, I just changed the letter. That's all I'm doing here. It should have been an x. So I took this, I broke the first part of it apart, and I used the power rule to take the minus sign and apply that first, and then keep the x on the outside. This is like our other problems. But here we're subtracting a 2, which is kind of like adding. So I'm going to multiply it by the base again, and this time raise it to that power. All right, so this is how I got from here to there. That's really messy. That stresses me out, sorry. Y equals, now we can fix this, and this becomes 2 to the x, and this becomes, let's see, we need to square it and flip it. So it will be times 4, right? This becomes 1/4 when we square it, and then the minus sign flips it. All right, and then the way that we want to write this is y equals 4 times 2 to the 2x. This is the preferred method for writing the function. And so what does that do to our graph? Well, we know that we're going to be going this way, but let's look again at what happens where is that place where we're going to cross over from positive to negative. Let's choose x equals -2. And our, oh, this should be, I'm sorry, this should be an exponent. Oh, I'm sorry, you guys, that's so messy. 4 times 2 to the x. I had it up there, I just copied it down there, and that was wrong. Okay, so this is going to be 4 times, what's 2 to the -2? It's going to be the reciprocal of 2 squared, which is 4. So the point where our curve will change is at -2 and 1. It's going to be right there. That's the place where it's going to get crazy, right? Where it shifts from this to tipping up faster. And so to find our second point, let's put in -3, or no, -1, sorry. I want to go one closer this way. John actually chooses 0, so let's just go with that, okay? This will be 4 times 2 to the 0 power. 2 to the 0 power is 1, so it'll be 4 times 1, and this will be 4. All right, so our other value is 0 and 4. 1, 2. My grid is way off on this. It'll be up here. Okay, so the first value I chose because I could see that was going to turn this into a 1. Okay, I guessed at this because I thought, okay, if I turn this into, I put a -2 there, I was imagining that, and I knew that would get me to 1/4, and I knew that would get me the reciprocal of the coefficient. So in choosing these values, you just have to guess. It's always a nice idea to try 0 for x, but it was this lead coefficient that forced me to play around a little bit with the numbers to try to get this. All right, that is the last one. I wanted to say, though, that this is also an important part of the problem, and I wanted to box these. When we adjust the original function to get rid of the complicated exponent and just have that cute little x up there, that is also, and here we had it. Okay? Let me know if these confuse you, and we can tackle them when we talk, or I can send you a review. Okay? Thank you. Goodbye.